We're going to move on now to Yuzhi Cai. He's going to talk to us about the Bayesian method for non-Gaussian autoregressive quantile function time series models.
Hey, good afternoon. So I'm going to talk about a Bayesian method for non-Gaussian autoregressive quantile function time series models. The outline of the talk is first I will talk about a quantile function and then introduce autoregressive quantile function time series models, followed by a Bayesian method to estimate the parameters of the model, and carry out some simulation studies to check the performance of the method, and also apply the methodology to two real-time series data, and finally give some conclusions and future work. So suppose if x is, we just consider continuous random variable. So for a continuous random variable, the distribution of that can be defined by a distribution function, can be defined by a probability density function, and it can also be defined by a quantile function, which is the inverse function of the distribution function. Okay. In most statistical modeling, we almost always use density function or probability distribution function, but not quite often we use quantile function. So what's the point? We use quantile function here. One of the reasons is sometimes, or we can say, you can see later, a lot of random variable has an explicit mathematical form for the quantile function, but not probability distribution function. Okay. So in order to use those type of distributions as a probability model, and then we need to know how to use those quantile functions. And another reason for that is quantile function has a lot of very interesting properties, and to deal with them is much easier than to deal with probability density function or distribution function. For example, sum of two quantile functions give us another quantile function. Product of two positive quantile functions give us another quantile function. And if we have two quantile functions, then the linear combination of them, if we take weight w, lie between 0 and 1, and that quantile function will lie between these two quantile functions. Okay. And also, if q of tau is a quantile function, then this simple transformation will give us another quantile function, and well, that tau is just a probability, so it lies between 0 and 1. So that means it's very flexible to construct new probability models, okay, if we work directly with quantile functions. So how can we use those quantile functions for time series models? Before we do that, we give some very simple examples. Okay. So for example, for the exponential distribution, the distribution function, we're all familiar with that, and the quantile function is just the inverse of the distribution function. So we can have an explicit formula for both functions. And for the power distribution, it's also easy to get the quantile function. And here, that tau again is the probability. Okay, so value lie between 0 and 1. For parental distribution, which has been used quite often in extreme value analysis, for that one, the inverse function can also be obtained if we combine power distribution and the parental distribution. Okay, because both quantile functions are positive, so we can get the power parental distribution. And in that case, we just the product of these two quantile functions. And for this distribution, okay, this quantile function, we cannot find its inverse function. So in other words, the distribution function of this random variable cannot be obtained explicitly. And perhaps that's one of the reasons this type of distribution seldomly used in practice. Okay. And how can we use all those quantile functions to deal with time series models? So we all know a usual autoregressive time series model is just given by equation 1. Okay, and we all know that. And here we have an error term, epsilon t here. And that epsilon t, we usually assume are independent, identically distributed random variables. And if we want to estimate parameters by using maximum likelihood method or use MCMC method, we need to know the probability and density function of that. And another thing is this model only gives us a conditional mean of yt, okay, conditional on the history up to time t minus 1. The question is, how can we estimate the conditional distribution of yt? Okay. One way to do that, to estimate the quantiles. So if we can use model 2 proposed by Conker, use that model, estimate the Tau's conditional quantile of yt given history up to time t minus 1. And those A0 tau, A1 tau, etc., those are the parameters of the model. Okay. And those parameters will depend on the probability tau. So for example, if tau equals to 0.5, we will have a conditional median of yt. If tau equals to 0.95, we have a 0.95 quantile of yt, okay, conditional on the history. And this model does not contain error term. So for each quantile, we use a certain method we'll discuss briefly later to estimate the parameter values. So because it does not contain the error term, we usually treat them as a semi-parametric model. And the parameters can be estimated by just by solving the minimization problems, okay, and the rho tau of ut is defined by ut multiplied by u tau minus I, that's an indication function. So ut just similar to the error term. And of course, there are different methods to solve that minimization problems. But there are some limitations for this type of quantile time series models. And once we have a sequence of quantiles, in fact, we have the whole distribution. Okay, so that's the point. And because the parameter depend on the value of tau, so if we want to estimate the whole distribution, conditional distribution of yt, we have a lot of parameters need to be estimated. And also the estimated quantile may violate the basic monotonic property of a quantile function. The quantile function should be monotone increasing, but use this method, sometimes you may find they are not monotone. Okay. And also, it is impossible or very difficult to use that type of quantile function models to estimate the extreme quantiles. The reason is once the tau approach to 1 or 0, we have less and less data available. So you will have difficulties in estimate the parameter values. To solve those type of a problem, we could just move on, try to estimate the conditional quantile function of yt rather than in a discrete version. So in this way, we have an error term q of tau and gamma. Okay, that's in equation 3. That's the quantile function of the error term. So for this model, okay, in fact, give us a conditional quantile function of yt. So tau will be any value lie between 0 and 1. So we have a whole function there. And A0, A1 until AK are the model parameters, which does not depend on the tau now. Okay. And there are several methods can be used to estimate the parameters, and which has been discussed in Gilchrist's book. And the last method, maximum likelihood estimation method. For that method, because now we know the quantile function, and we can even assume we do not have an explicit mathematical formula for the probability density function. So if you use the maximum likelihood estimate, there are some difficulties involved. Okay. So, and that's why later, and we will propose a Bayesian method to try to estimate the parameters in this type of model. Before doing that, let's look at some simple autoregressive quantile function time series models. So in fact, we could just replace the error term by different quantile functions. So for the first, we can have exponential quantile function model. So we use the exponential quantile function. And for the parental quantile function model, we use the parental quantile function as the error term. And for the power parental quantile function, and we use the power parental quantile function at the end of this type of time series model. Of course, in this talk, and we only deal with the linear form. Okay, so that's the first part of the model. And the Bayesian method to estimate the model, which will be discussed later, apply to any of these type of models. But to simply find the explanation, we focus on the first, just the exponential quantile function models. So that's the model we consider. And we let beta be the model parameter vector. So put all the parameters there. Although we do not, or we assume we do not have an explicit formula for the density function of the random variable. Okay, but the density function can be expressed by f of x, that's the density function of x, just equals to 1 over the derivative of quantile function, okay, with respect to value of tau. So that means density function may not be able to be expressed as an explicit function of x, but it can be expressed as an explicit form for tau. Okay. And how can we use the data? So we have the conditional likelihood of the data y of t. Okay, if we that conditional on the initial several observations, that's a product of the density. And each density can be expressed by using the quantile with respect to tau. So the information of the data can be included in a way such that we need to solve equation 4 for each of the data yt. If we can solve that, and then we just put the tau of t in the likelihood expression, then we have an explicit formula for the likelihood function. And of course, for this simple model, we can solve tau explicitly. But for example, if we take the power parental quantile function model, and then we cannot solve equation 4 exactly, we have to use some numerical method to solve the value of tau. And then we can obtain the posterior density function and assume the prior distribution for the parameters, just a pi of beta. And omega is the parameter space. And furthermore, if we assume the prior is independently, the prior density function equals to the product of all the priors for each individual, and the pi of AI will be the normal density function with zero mean or some variance. Okay, and pi of gamma, that's the last parameter in the model, and that there's a type error here. So the pi of gamma is e to the negative alpha of gamma. Okay, so if we take exponential prior for this parameter, then the posterior distribution is well defined on this parameter space omega. Okay, so for different quantile function model, this parameter space may be different. So we need to do some modifications to deal with other quantile function models. And in fact, here we only take a special prior. We say, okay, for the normal, for the AI, and the exponential for the gamma, those parameters. But in fact, for the posterior distribution to be properly defined, the prior density function for the AI can be any, as long as it's proper. But for the gamma, the prior distribution should be chosen such that the posterior be well defined. Okay, so that's the thing we need to be careful. And because the likelihood function, okay, now is expressed in terms of tau. So tau, in fact, is a function of the parameters. So it's quite difficult to design or use a Gibbs sampler to estimate the parameters. So we need to think about general metropolis Histine method. And here we only just design a very simple random walk sampler, try to estimate the parameters. And the main thing here is for each, once we get the proposal from the G, we need to solve equation for tau t prime. Okay, so for each of the parameters, we need to solve that equation and put that into the posterior distribution, and then we can calculate the acceptance probabilities. And in this case, we still just take a simple form proposal and try to get the proposal from normal distribution. Of course, you can use others and try to find a better sampler. So the method is quite straightforward. What's the performance of the method? So we carry out some simulation studies. So that's the true model. Okay, we can obtain a sample from this model. And this gives us the time series plot of the simulated data. And that's the ACF plot. That's the partial ACF plot of the simulated data. And for the prior information, the experience shows that for the prior sigma and AI, of course, so for that type of, because and the larger the value of that will decide the how strong your prior information have. But it looks like for this simple sample, the method does not depend on the prior a lot, but we need to be careful about the initial values. We need to guarantee the initial value should lie in the parameter space, and that's one way to decide the initial values so that you can start your sampler. And then we can just do a standard job and collect the samples. for this one, that's the histogram of the collected samples. And here we have a vertical line, and we also have a dashed line. Vertical line stands for the true value of the parameters. Dashed line stands for the estimated or Bayesian estimate of the parameters. And from here, we can see the true value of the parameters lie well within the posterior marginals. So that's the fitted model. And we can compare the fitted model with the, not just the estimated value, we can further compare the fitted conditional quantiles with the true model. And here we plot the fitted conditional quantiles from the fitted model and the true model. And it seems I can't make it larger. In fact, we should expect we have, because we estimate, just draw those 4 quantile curves. And one from fitted, one from the true, so we should expect 8 curves there. But because those 2 models are very close, so we just can't see the difference. We only can see 4 of them. If I make the figure larger, you can see somewhere here, only in the extreme quantiles, and then you can see there are slight difference between true and the estimate. And we also mentioned semi-parametric approach. For this model, it does not depend on the error term. So this model we can also use this model for the simulated data. So no matter where the data come from, this model should be okay. Okay, we can apply that. And we use the free statistical software R to estimate the model. Okay, that's the semi-parametric model. And then we also compare the fitted conditional quantiles from this semi-parametric model with the true model. And then you can see, so that's for the 0.05 fitted conditional quantiles. That's 0.5, that's 0.95. There are slightly, now you can see some difference here, but for these 2 looks fine. But for the extreme things, when tau equals to 0.995, and the difference becomes quite large now. So that's the semi-parametric. And we also, in fact, we fitted this type of model with different orders and produced the residual quantiles against the quantiles of exponential distributions. For the first, so that for the order equals to 0, that's order equals to 1, 2, 3, 4. Okay. So when order equals to 2, 3, 4, they look quite similar, but for these 2, looks like not a good fit for these 2. And we also calculate the AIC values. Of course, I should say, it's not, strictly speaking, it's not appropriate to use AIC in this content, but anyway, it gives us some idea about the penalty on the number of parameters in the model. And for this AIC value, we can see order equals 2. So for that model, and gives us the minimum value of AIC. So all that suggests this simple method and enable us to find the proper model here for this simulation study. Now we apply this model to the data. So that's the level of Lake Huron time series between 1875 1975 to 1972. And we plot the time series, and we produced the ACF and partial ACF plot, and it looks like show a similar pattern as the simulated data. Okay, for the this part it decreased quite slowly, but that decreased only have several spikes at the beginning. So we just tried to fit this type of quantile function models to estimate the conditional quantiles of yt, the data, and that's the fitted model is given by equation 8. And we plot, again we plot the sample, looks like not that stable, and also there's some curvature on this part, so there's some doubt on the fitted model. But we also considered the semi-parametric approach and to see what happened to this type of approach. And then we do some comparisons on the result. One is from the parametric model, one is from the semi-parametric model. And that's the fitted conditional quantiles for those several quantiles. Okay. And from those things we can see, so here the dark curve represents that's the true time series plot. And for this one, that's the conditional fitted conditional quantiles from the parametric model. That's from the semi-parametric model. And as expected, for this one, there are some crossing happened in several places. Okay, so that's the if we use the semi-parametric approach. And if we just pick up two conditional quantile function of y7 or y33, we just pick up any two of them and produced the quantile function. And those continuous, the light continuous curve are the conditional quantile functions of y7 and y33, and dark curve correspond to the quantile functions obtained from the semi-parametric approach. And again, it shows us some non-monotone behavior on the quantile functions. And we also applied the method to the DEX index, and that contained just 400, and during 1995 to 1996. The time series plot, obviously there's not stationary, there's an upward trend, and then at the end it comes down. And the ACF plot and partial ACF plot. So similar pattern here as the simulated data. So we just try this model. Okay. And for this one, again, so we have the first plot is the quantile QQ plot and some doubt at the end, and that's the collected samples. And here looks like there are two peaks. Okay. So probably cause that maybe need further identification for this result. but anyway, we get the fitted model with this error term. We haven't tried some other quantile function models, okay, but just to show the result here. And for this one, we consider forecasting. So we have estimated a quantile function, and we can obtain the condition. We're conditional on the history up to time 400, so that's the observed data. And we can estimate the predictive density function for the next time point. We can estimate the predictive median of the time series at next time point, and the predictive mean, because we have the whole distribution, so we can have any quantity of interest. And then we can also compare the result with the actual observed value. And in this plot, the curve is the conditional density function of yt at t equals 401, and the solid curve gives the position of the true observed value, and dotted curve in the middle gives the conditional mean of y401, and the dashed gives the median of that. And in fact, for this data, if you just fit a Euro ARMA model, okay, and because that Euro ARMA model will give us the predictive mean of the y 401. Okay, so and if you actually do that time series model, and then you will find the predicted value for that one, but you need to difference once, and can provide a better result there. But the thing is, for this one, and we can have a whole distribution of the predicted for the distribution for the DEX data at the next time point. So that's the basic thing involved here. And all these are very initial work, okay, and there are a lot of work can be done to carry out further research. And the methodology developed here can be applied to many other quantile function time series models. And the methodology developed here can also be generalized to deal with nonlinear time series, to handle the case where the scale parameters of the model also depend on the value of the time series. And we also need to carry out thorough comparisons between the semi-parametric approach and the parametric approach. And the comparison between the quantile function approach and the distribution function approach, and these two types of approach also need to be carried out in the future. And also we need a new methodology need to be developed for the forecasting, because remember, when we write out the quantile function models, that model does not represent a data generation process. So we put the observed data into model, we only get the quantile. Okay, so that's, you can't just recursively use that into the model. So in that sense, of course, we can do a simulation, just like the last example we carried out forecasting for the next time point. If we just continue to the, and then once we get the predicted density function, we can generate another sample, and then put that sample into the equation, and then in this way we can move step by step into the future. But we also need some other maybe better method for the forecasting. And for this one, we also need to, for example, to generalize or develop a new methodology to deal with multivariate time series. And some of the work has been done and need to be reported as well. And finally, I would like to thank for the invitation and the financial support which made it possible for me to present the result here. And a big thank you for you all for your attention.
Any questions? Use my usual hosting question then. So if I understood it correctly, at least in this exponential case, you could actually explicitly write down the density function in that case.
Yes.
Because you can actually analytically solve it.
Yeah.
So in fact, it seems like it just corresponds to a different, perhaps rather complexly parameterized density function. At least in that case. I mean, I guess there are examples where you cannot do that, but are you not really in principle just doing the same kind of thing that we always used to do, but just with a very complicated density function?
And in fact, the main point here is we should not just use, for example, this type, because once if a distribution has an explicit form for the densities, we can use all the non-usual method. But the thing is, for the quantile function approach, for example, if your data have some different features, you can use different quantile functions to model different features and then combine them to get a combined distribution. But that will be your error term. So that will make it possible for you to establish a proper time series model. And here for the exponential, it's just a special example here. But if you use different quantile function and combine them in a proper way to get a new quantile function, and then that quantile function usually do not have explicit form for the density function. So in that case, usual method will not work. So in that case, this approach certainly will work.
More questions? Okay, let's thank the speaker once again.
Okay, thank you.